All right, welcome back. So this is thermodynamics 2, homework 2 number 1. So homework 2 is with both what drives processes with respect to Gibbs free energy and Clausius-Clapeyron problems, or Clapeyron problems in general. So that it's kind of a mix of both. So the first one says, explain why polymethylmethacrylate, so that's PMMA, is not soluble in water, even though methylmethacrylate, just MMA, is somewhat soluble in water in the context of Gibbs free energy. In other words, during the polymerization, the polymer separates and floats to the top. So what happens? And I'm just going to draw them as little circles. So you got this methylmethacrylate, you got this methylmethacrylate, you got this methylmethacrylate, and then you got all these waters, okay? And so the methylmethacrylate is somewhat water soluble. There's some hydrogen bonding groups, so it does like the water somewhat, okay? But as soon as these start to link up, it becomes less and less soluble until it just separates completely from the water, okay? So why does this happen? I mean, it's not like as soon as it polymerizes, it's interacting with the water any differently. I mean, in a sense it is, but, there's still just as much hydrogen bonding. But what happens that makes it so it doesn't want to be in the water, or rather, why the water doesn't want it with it? Okay, so, and that's my whole philosophy on these kind of things, is water, things are not hydrophobic, okay? Water is just xenophobic, okay? And, water loves the hydrogen bond, and if you disrupt that, it ain't going to be happy. Now here, in this kind of context, I lost my red marker. So in this kind of context, it's easy to, there's still a lot of hydrogen bonding between waters and stuff, and then slightly hydrogen bonding with the methylmethacrylate itself, okay? But as soon as you form this bond, you kick this water out and break these hydrogen bonds. And eventually you have this big glob of polymer, making it that much harder for the water to hydrogen bond with itself. So, in the polymerized state you have this guy, whereas in the non-polymerized state, there's, it's only taking up this much volume. Okay, so you got this much volume being taken up versus this much volume. And so what you have is an exclusion of space. Okay, A, and B, these can't hydrogen bond with itself as well because, well, there's just too much of it. It breaks up the hydrogen bonding, and so it just says, oh, well, because I can't get enough, I can't get water in here, so to speak, I'm just going to kick this whole polymer out, and then I can hydrogen bond with my buddies again. Okay, so that's what happens, and that's why it happens. It's not so much the interactions, it's because it's taking up all this volume, okay? And so, in terms of Gibbs free energy, why does that happen? So if I think about my decision tree, okay, so I have my decision tree that says, okay, first off, does it happen? Well, I already told you it happened, so yes, it does happen. Okay. And then I ask myself, yes, okay, what about the entropy? Well, you've got polymer, we're not talking about the actual polymerization. We're just talking about why doesn't the polymer stay in the liquid phase? Why does it phase, why does it float to the top, as it were? Okay, so you've got a couple things going on in terms of entropy. Now think about it. You've got, typical chaos things, okay, but you got to think about like okay, is there different phases? Okay. Well, I'm going from kind of two liquid phases, liquid polymer and liquid water, and solid polymer floating on the top, and liquid water. Okay. Well, it would rather be in the liquid phase, right? Okay, so that's one thing. Also, in terms of mixtures, what mixtures? Are they entropically favorable or are they entropically disfavorable? Yeah, you want to be mixed when it comes to entropy. So that's another thing that's against entropy. The other, however, that all gets kind of counteracted by that exclusion volume. Okay, because there's that other piece associated with entropy called configurations. Okay. Let's think about the room that I'm in right now. Okay, so right now, I can't be in the center of the room. Essentially, there's an elephant in the room. There's something so big in the middle of this room, all I can do is hug up against the wall. So, hug up against the wall. That's all I can do, because there's just this huge thing, in this room. Okay. But if I kick it out, okay, well, it's free to move how it wants, and I'm free to move how I want as a water molecule. Because now I can be in this space. Now I can be like this, with the polymer up here. Okay. So yes, it's not mixed, but it wasn't really mixed beforehand. It was pretty much like polymer phase, water phase. It's not like there's waters really in the middle of here. So the mixture issue, not really an issue. Okay. Here, it's actually more entropically favorable for the system as a whole to phase separate it. Because I've just created that many more configurations allowable for the water. And I pretty much have the same configurations for the polymer, because the polymer is not going to do much. It's going to stay entangled in this manner. But the water, well, now it has so many more options, okay? It's able to really get in there, okay? So that's one thing. And so this actually increases. Okay. So it is actually more entropically favorable for this to phase separate as a whole. Okay. So then I have to ask myself about enthalpy. What about the interactions? Well, we already said that the interactions are pretty much the same. Except for I can have a better hydrogen bonding network when that polymer is not in the way. Again, think about it in terms of the elephant in the room and I'm water, okay? It is a lot easier to hold hands with my buddies when there's not a big fat elephant in the room. If the elephant is in the corner of the room, well, it's a lot easier for me to hold hands with everybody. So actually, enthalpy goes down. Okay. Because in terms of the water interacting with the polymer, that hasn't changed, but I'm able to have a lot more hydrogen bonds between water with the polymer not in the way. So this is actually driven by both. Okay. So it's driven both entropically and enthalpically. And that's one.